Alright, in the last video we ended with looking at ionic bonds, and now we want to look a little bit closer at covalent bonds and compare some of those properties that we get when things are sharing electrons. So to begin with, when we have atoms in non-ionic compounds, they're going to share electrons. They're not going to gain and lose like they do to become a cation or an anion. And the chemical bond that actually results is called a covalent bond. Excuse me. And then those atoms that are sharing electrons form a molecule. So molecules have covalent bonds in them, and molecules look different than the crystal lattice that we saw of the ionic bond. Now, there are 7 elements that are found in nature as diatomic molecules, meaning they are found as their element bonded to another atom. They're not found as individual atoms, and those 7 elements are hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. And yes, you do need to memorize those 7 elements that exist as diatomic molecules in nature. Alright, so let's look at how these things are sharing electrons a little bit closer. So if we take 2 fluorine atoms, you can see that they both have 7 valence electrons. So what they're going to do is they're going to share their 2 unpaired electrons down here, and we're going to refer to that as a bonding pair of electrons. They are being shared between the fluorines, so now both fluorines have an octet. They both have 8 electrons around them. And then these other pairs of electrons that were already paired, that are not involved in bonding, those are called lone pairs, and that's a very important term, so circle that, put a big star by it. We need to make sure we know the difference between lone pairs of electrons and bonding pairs of electrons. All right. So let's take a look at some of these sharing that goes on between atoms. So when only one pair of electrons is shared, what we get is called a single covalent bond. And we can represent a single bond either with 2 dots like that. We can also use a line, so a dash between the 2 hydrogens to represent a single bond. If 2 pairs of electrons are shared, like between the oxygens in oxygen gas, we can show 2 dashes or 4 electrons being shared between the oxygens. We call that a double bond. And a triple bond forms when 3 pairs of electrons are shared. So here, the nitrogens in nitrogen gas are going to share all of those electrons. So you can draw 3 dashes, or you can draw 6 electrons. Most often you're going to see the dashes used rather than the dots to represent the double, triple, and single bonds. So those are the ones we're going to be using in class. Alright, so we're going to learn more about how to draw all of these compounds in class, so you don't have to worry about that part of it, but we do need to talk about how to name them once we know the molecular compound, and it has to do with the formula that's given. So when you're naming a molecular compound, which has covalent bonds in it, the first rule is you're going to name the first element with its entire element name. Okay, so for our example, N2O, the symbol for N is nitrogen, so the first part of the name is nitrogen. The second element, we're going to use its root, and we're going to change the ending to "ide." So O is oxygen. We're going to change it to oxide. And then we're going to use prefixes before each of the element names to show how many there are. So the prefix for 2 is di, so we would say dinitrogen, and then there's 1 oxygen, so monoxide, dinitrogen monoxide, okay? The only kind of little rule is if you only have 1 of the first element, you don't use mono at the beginning of the name, so you can skip over the mono part, but you do use mono if there's only 1 of the second element. For the next example, let's take a look at the covalently bonded P2O5 molecule. All right, so we have P2O5. P2O5, and we want to know what its name is. So P is the element phosphorus. The prefix for 2 is di, so we would say diphosphorus. And then O is oxygen, and we change the ending to "ide." And the prefix for 5 is penta, so pentoxide. Okay, so that would be our name for P2O5, diphosphorus pentoxide. All right, before we look at these last few properties, there is one thing I want to note. Your summer assignment, part of what you had to do was memorize a list of polyatomic ions. There are covalent bonds within those ions, and you are going to need to know them for this unit and from now on. So for all of you that have been asking me, when do we have to know the polyatomic ions? The answer is now. So make sure you get your list out, start reviewing, and we will be using all of those names and formulas starting in Unit 5 and continuing on through the rest of the year. So now is the time to know your polyatomic ions. Okay, so let's end by talking about some properties of covalently bonded compounds compared to what we saw with ionically bonded compounds. So covalent bonds between the atoms are strong. So within a molecule, those are really strong attractions, but the attractive forces between molecules are weak. So from one molecule to the other, intermolecular attractions, those are relatively weak. And those weak forces between the molecules are going to give them very specific properties. For example, covalently bonded compounds or molecular compounds have relatively low melting and boiling points compared to ionic compounds. They're going to be a whole lot lower. A lot of the molecular compounds will be soft, so if you hit them with a hammer, they might bend. Things like wax and plastic and things like that that are not crystalline are going to be really soft in comparison. And there are some molecules that will align themselves into a crystalline structure, but because their particles are less attracted to each other, they're going to have lower melting points than the ionic compounds do, even if they happen to look like a crystal. For example, sugar looks like little crystals, but it is molecular, it is not ionic. And then this slide doesn't specifically say it, but solubility kind of varies. There are some covalently bonded compounds that can dissolve in water and some that cannot. It has to do with polarity, which we will get to a little bit later on in this unit. So whether something can dissolve in water or not doesn't necessarily make it covalent or ionic, but the difference is when a covalent compound can dissolve in water, its solution that it makes will not conduct electricity. So we might want to add that on to our notes here, that the solutions are non-conductors. So we said ionic compounds, if they dissolve in water, they will be able to conduct electricity because of the free moving ions. But if a covalent compound can dissolve in water, it's going to have free moving molecules, and those molecules don't have a charge, which means they can't conduct electricity. So solutions of molecular compounds do not conduct electricity like ionic compounds do. That would definitely be a good way to tell the difference between an ionic and a covalent compound, is whether or not the solutions conduct electricity. All right, so we're going to be starting out this unit with a lab that compares all these different properties that we've been talking about, melting point and solubility and conductivity and crystalline structure and all those different things. So make sure you have your lab notebook ready to go for Tuesday, and make sure you bring your notes for Wednesday, because we're going to be taking some notes in class on Wednesday on how to draw all of the dot structures of more complicated molecules than what we saw in the notes.